Hello, you're welcome back. All right, so now we're gonna continue, okay, from where we stop, with light, and here we're gonna be looking at the refraction of light. Okay, so we've already talked about the reflection of light, so here we'll be talking about the refraction of light. Now, light is said it always undergo refraction, okay, when it actually moves from one medium to another. All right. For example, let's say you have two medium. Okay, light is coming from A, which of course is a less dense medium. Then the light rays from A enters into another medium, let's say water. Okay, due to the difference in density, because water is of a higher density than air. Okay, then what happens to the light? The light rays actually bends. So that change in direction of light as it moves from one medium to another is what we called refraction. Okay, and of course you know very well that we'll measure the angle. This line here, okay, is of course is the incidence. The angle between the incidence and of course the normal is the angle of incidence. We know that already. Okay, but here now we are having the angle of refraction. The angle between the refracted ray and the normal is the angle of refraction. Okay, so now from what we have already, okay, we can actually state the law of refraction. And this law of refraction I want to state now was actually is known as Snell's law of refraction. Okay, so it's Snell's law. Okay, now the law actually states that the ratio of side of the angle of incidence, that's sine I degrees, all over the side to the side of the angle of refraction, okay, is always constant in any medium. Okay, in any medium where that refraction actually occurs, and that particular ratio, this ratio is what is regarded as the refractive index of a medium. Okay, so this ratio is what yields refractive index. So every medium has its refractive index. Okay, and of course we use this symbol to represent refractive index. All right, so refractive index of a medium is always giving us the side of the incident angle to the side of angle of refraction. Okay, so I hope that is well understood. Now this is one formula for refractive index. Okay, there's another way of expressing refractive index. The refractive index of a medium is giving us the real depth of that medium, then divided by the apparent depth. Okay, real depth of the medium then divided by the apparent depth. It is noticed that anytime refraction occurs, okay, there are some certain phenomena will be observed, and that phenomenon is that when you look at the actual depth of that particular medium, okay, the actual depth you see that you measure is not going to be what you see when you look at it from from the refracted ray of light that actually leaves that medium. Okay, I have to illustrate what I mean. Let me illustrate. Let's say you have a container of water. Okay, now this container of water at its depth has, let's say, an object that you want to view from there. Okay, and the container actually contains water. So let's say you want to view this this object. So now definitely the rays of light from the object as it reaches the surface of the water, now as you can see, it is passing from a dense medium to a less dense medium. Okay, so what you will notice is this. Of course, it will actually refract, it will bend, refraction will occur, refraction will also occur in this case. Now if the viewer that is actually view, okay, based on this ray that actually refracted, because the viewer will view this particular object at this depth based on the rays that actually refracted, okay, coming out from the water. If this viewer should actually view, okay, then definitely what the viewer will see, if I trace it in a straight line, because the image will be formed when these two straight line, okay, at the point where they intersect, that is where the image will be formed. So that means this image now, if this viewer should actually view it, will be formed at this depth. Okay, so that means this depth, that is not the actual depth. Okay, when the person sees it, it will seem as if the water is shallow, and of course this object is actually at a very shallow depth of the water, and that's what we call it the apparent depth. Okay, the apparent depth. Okay, now meanwhile, from this point to this point becomes the real depth. Okay, this better be from the, if you measure the actual depth of this, so that will be from this point to this point becomes the real depth. So you discover that the object, now there's a displacement between the actual depth of the container of water, okay, to the apparent depth. So this is the displacement. So the distance from this point to this point, that becomes the displacement. So there's always a displacement due to refraction. Okay, so how do I get this displacement? Now this displacement that is actually produced, the displacement of that object can actually be calculated by subtracting the apparent depth from the real depth. Okay, so let me use ROD to represent real depth. Okay, then of course AD to represent apparent depth. Okay, so I hope that is well understood. Let's look at an example. Let's say this medium, okay, is actually made up of water. The refractive index of water is constant, of course, is 1.3. Okay, and let's say that we have this container. Okay, the depth of this container is 20 cm. All right, so okay, so let's look at a situation where you are being asked to find the displacement. Okay, the displacement. Now, if you have to find the displacement in this particular trough container of water, first of all, you need to get the apparent depth. Okay, I already have the real depth. So how do I get the apparent depth? The refractive index of course, you know, is the real depth equal to the real depth all over the apparent depth. Okay, so that's going to be equal to here as 1.5 is the refractive index. The real depth is 20 cm. Then apparent depth is what I'm looking for. So if I should make the apparent depth the Sorita formula, that's going to be equal to 20 divided by 1.5. Okay, that will give 50 cm approximately. So with this now, I can find the displacement. Okay, So that way the displacement will be equal to the real depth, which of course is 20, minus the apparent depth, which is 50. So that gives me 5 cm. So that is the displacement. So don't forget the formula, okay? Refractive index is also expressed as real depth all over the apparent depth. So I can call this formula 2. Now there's another way of also expressing the refractive index of a medium. Okay, refractive index of a medium can also be expressed as the velocity of light, in air then divided by the velocity of light in that medium. The reason being that, okay, anytime light undergo refraction, then the velocity actually changes. In fact, what causes refraction is the change in velocity, because that light is moving from a region of different densities. Okay, due to that, the velocity will change. So refractive index can also be expressed as velocity of light in air, then divided by the velocity of light in that medium. Okay, that's another way of expressing refraction. All right, so now we are going to study refraction using different medium. One of the very first medium we are going to look at, or the medium we are going to consider, okay, the only medium we are going to consider is called prism, or glass prism. Okay, so we are looking at the refraction of light through a glass prism. Refraction in glass prism. Okay, of course there are two type of glass prism we are going to look at. We are going to look at what the rectangular block, okay, rectangular glass prism, and of course we look at the triangular glass prism. All right, now let's start with the rectangular glass prism. Okay, it's simply a thick glass. Okay, a thick glass that actually deviates rays of light as it passes through it. Okay, so here, rectangular. Okay, so now how do we actually represent refraction in a rectangular glass prism? First, we need to draw a number. Okay, so after we must have drawn a number, then we actually measure some angle of incidence. Okay, angle of incidence. Then this angle of incidence we can actually use optical P, because if I have gotten my angle of incidence, it is not, I cannot measure my angle of refraction unless there's the ray of light passes. I actually measure the ray of light that passes through this prism. Okay, and the only way to measure the ray of light that passes through this prism is to be able to, I have to see it through the other side of the prism. That means invariably I have to put objects, okay? I have to use what is known as optical pin. Optical pin, I have to place optical pin at a different point along this angle of along this incidence line, right? Then I have to go through the other side of the prism and locate, okay, the refracted image. Why? Because the image of this prism will be formed through, I will see it through refraction. All right, so I have to actually trace it. So if I should trace it, that means from the other side of the prism, okay, I'm gonna have, and the rays will definitely emerge after it must have refracted. So I have to measure the emergent ray, okay, that actually come out of the prism. This is the emergent ray. So it's only when I now measure the emergent ray that can now join the two normal. So these two normal now will be able to give me by angle of incidence, angle of refraction, okay? Of course, it's also equal to this angle of refraction. They are equal. Alternate angle are equal, right? So this is how refraction occur in a rectangular glass prism. All right. For example, let's look at some situation where, okay, let's say this prism, what I measured as the glass angle is 60 degrees. Okay, the refractive index of glass, okay, glass prism is 1.5 approximately. Refractive index of glass prism is 1.5. Okay, let's say having this glass angle 60 degrees, we are being asked to find the angle of refraction. Okay, angle of refraction. How degrees? Question mark. So how do I do that? Of course, for me to do that, I will apply Snell's law. Refractive index is equal to sine of incidence divided by sine of refraction. Okay, so this is going to be equal to 1.5 is equal to sine of the incidence. What's the incidence angle? Of course, what I have here is the glass angle, and you know very well that, okay, for me to get incidence from glass angle, you have to subtract the glass angle from 90. Okay, that's going to be sine 90 minus 60, right? Then divided by sine r, which of course is sine, that's going to be sine 30 all over sine r. So I have to cross multiply, okay, to make sine r the subject. Sine r now is going to be equal to, if I arrange this equation, that's going to be equal to sine 30 all over 1.5. Okay, sine 30 is 0.5 already. Then divided by 1.5. If you do this division, you have okay, let's do that division. Calculator. 1.5 divided by 0.5. Please pardon me, 0.5 divided by 1.5. That's 0.3. Okay, so I'm having 0.3. So invariably, now to get my angle of refraction, I will have to find the sine inverse of 0.3. Okay, so shift sine inverse of 0.3, that's 19. So my angle of refraction is approximately 19 degrees. So I hope that is well understood. All right, so now let's look at how that works with a triangular glass prism. So how does reflection actually occur in a triangular glass prism? Now, a triangular glass prism is actually thick glass, okay? That is two faces. It has two faces, okay? The two faces are actually a triangle. Two triangular faces. Of course, I can actually, this is what, so a variable is a glass as thick as, okay, what I have here, right? A thick glass. So there are two faces, both the front face and the back face are triangle. So for me to represent that, I'll simply just use a triangle, and this triangle, okay, is equilateral in nature. That is why basically it's called, the triangular glass prism is called an equiangular. Okay, why? Because the triangle is actually, the triangle face is an equilateral triangle, so it's called equiangular prism. And of course, you know what about an equilateral triangle? All the angles are equal alongside the sides. So all these angles are equal, and I use A to represent it, A. Okay, basically in the laboratory, these angles, the angle of this, of the triangular prism used in the prism, this apex angle is basically 60 degrees. Okay, that's what you have. All right, now how does refraction actually occur in a triangular prism? First of all, I have to draw a normal. Of course, you should know that, okay? Now, why do I have to draw a normal? Now, the normal does not represent any ray of light. In fact, any ray of light that actually passes normally, okay, or symmetrically through the prism, ray of light that passes normally is a ray of light that is actually that's symmetrical. So any ray of light that is actually that passes through the prism symmetrically does not refract. It doesn't. It just passes like that, undeviated. It doesn't undergo refraction. Okay. So that is why I can only use this to represent the number, so that I can measure my angle of incidence. So I can now measure incidence. Okay. I can measure incidence. So incidence angle. How do I get to evaluate by angle of refraction? The same thing I did, okay, with that of a rectangular prism. I have to trace an object, optical pin, from the other side to know where it comes out. Okay, I will draw another number here, so I have to, all right, get to know where this actually comes out. So joining the two actually yields my refraction. All right, so also there's another this is the part where the ray emerges out of the prism. This part it enters. Okay, so this is of course another R. They happen that if I should extend this line where the intersect, okay, in fact, let me not go into details with the diagram, but let's just look at what we have. So this is the angle of refraction and this angle of incidence. That's another angle we measure in a triangular prism. Okay, that is what is known as the angle of deviation. The angle of deviation in a prism. Yes, there's always angle of deviation. The angle of deviation is the angle between the initial direction of the ray and the final direction. Now, this is the initial direction of the ray, of course, quite well. I've extended it. Okay, then of course, This is the final direction of the ray. So if I join it, the point where the two actually intersect, where two of them intersect, okay, gives you what is called the deviation. All right. So now, to get the deviation in a triangular prism is simple. You subtract 2 times r from 2 times I. 2r from 2I, okay? Because of course there's gonna be in a triangular prism there's 2I, because this side and this side represent I. There's also 2r, okay? So there are two refraction if you look at it from the two faces of the triangle, and there are also two incidence if you look at it from the two faces of the triangle. So the difference between the two refraction minus the two incidence gives you the deviation, okay? But it happened that, okay, the 2 times refraction is always equal to the, okay, the angle, the base or the apex angle of the triangle, the equilateral triangle, okay? So please take note of that. If that be the case, then I can simply say that, okay, the deviation is given as 2I minus A. So why am I doing this? I want to express another way of the formula for refractive index of a triangular prism, okay, based on deviation In fact, we used to call it the minimal deviation of a prism, okay? We call it the minimal deviation basically of a prism. So how do I get the relationship between the refractive index of a prism and the deviation of that prism? Now, first of all, I'll have to get my refraction. Angle of refraction from here is going to be equal to A all over 2. And of course, the angle of incidence from here, if I should make it the subject, okay, if I should make this 2I, of course, is going to be equal to D minus goes over because plus A. So that means the incidence that is going to be equal to the deviation or even the minimal deviation plus A, then all divided by 2. So having gotten the R and I can now apply this law. So that means the refractive index, okay, the refractive index of, please pardon me, okay, the refractive index of a triangular prism based on its minimal deviation, of course, you know it's always given as psi I all over psi R, okay? So that is going to be psi by I is the minimal deviation plus A, then of course divided by 2 all over psi R, which of course is psi A all over 2. It's very important. Now let's look at some typical example, okay? Let's look at a situation where, of course, you know very well that the refractive index of a glass prism is 1.5, okay? So let's look at how to get this the minimal deviation of a triangular, okay, glass prism. Knowing quite well that the refractive index is 1.5, and of course this apex angle, okay, is 60 degrees. How do we get the minimal deviation? Let's do that. Okay, from this formula that we can have, of course, refractive index is 1.5. Then the side of the minimal deviation, that's what I'm looking for. Then plus 60 degrees, all right, then divided by 2. Okay, so Then I have side 60 all over 2. So I'm having 1.5 to be equal to side the minimal deviation, or better still, let me cross multiply. Okay, I'll cross multiply it now. Side 60 all over 2, 60 all over 2 is 30. So if I should cross multiply, but it is all over 1, so I will have it side the minimal deviation plus 60 divided by 2, alright, times 1. Of course, it's still the same. Then cross multiply, I'm gonna have 1.5 times side 30. Okay, so let's work on this. So of course you know very well that if I should do side 30 is 0.5. 0.5 multiplied by 1.5, that's 0.75 actually. 0.75. Okay, so now you know very well that if I need to find the angle of this side, remember the whole of the minimal deviation plus 60 all over 2 is the angle of the side. So to get this entire angle, you know what I will have to do? Okay, I have to find the sine inverse of both sides, or the sine inverse of the other side. So I'm looking for the sine inverse of 0.5. So that means the minimal deviation plus 60 divided by 2. Okay, so let's do that. The sine inverse of 0.75, please. That is 48.6 approximately. Okay, so of course you don't have to cross multiply, right? Times 2. 48.6 then multiply by times 2. That's 97. So I have the minimal deviation plus 60. Remember, I've already cross multiplied. That gives me 97. Okay, so that means the minimal deviation now is going to be equal to 97 minus 60. Alright, so what does that give me? That should be what? 97 minus 60 is 37. 37 degrees. That's it. Okay, so I hope that is well understood. So we'll look at more questions in the next video, right? See you in the next video. Thank you.